What if AI could not only write essays for you, but also understand the nuances of a chess match? Welcome to AI by AI, where we dissect the latest breakthroughs pushing the boundaries of artificial intelligence.
Exactly. Today we're diving deep into 5 fascinating papers. First, we'll explore how AI is grading essays and understanding argumentative writing. Then we'll tackle the challenge of AI watching and understanding really long videos. After that, we'll see how AI can learn to describe games so well that other AI can play them. We'll also be looking at a system that automatically improves AI models over time. And finally, we'll check out a new AI model that's specifically designed for scientific discovery. Buckle up. It's going to be a wild ride.
And don't worry if some of these terms sound a bit technical. We'll break everything down in plain English. Think of pre-trained language models, or PLMs, as AI that's already been taught a lot about language, like a student who's done their homework before class. And reinforcement learning is like teaching a dog tricks. You reward it when it does something right. Let's jump in. Okay, let's dive into this research on machine-assisted writing evaluation, specifically how pre-trained language models, or PLMs, are being used to analyze argumentative moves. It's fascinating stuff.
Definitely. So the core idea is using AI to assess argumentative writing. Why is this important? And what are argumentative moves anyway?
Argumentative writing is crucial because it involves complex cognitive skills like logical reasoning and acknowledging different viewpoints. Argumentative moves are the specific strategies writers use to build their arguments. Think of them as the building blocks of an argument. This study looks at things like claims, data, counterclaims, rebuttals, and even non-argumentative text.
Got it. So instead of teachers manually analyzing essays, they're trying to automate the process with these PLMs. What were they doing before, and why is it a problem?
Exactly. Traditionally, it's been a lot of qualitative analysis and manual coding, which is time-consuming and hard to scale. This research points out that these methods limit efficiency and generalizability. Imagine grading hundreds of essays and having to manually identify each argumentative move. It's a huge task.
That makes sense. So what exactly are these pre-trained language models? The paper mentions BERT. How does that work?
PLMs are machine learning models trained on massive amounts of text data. They learn to understand not just individual words, but also the context of words within sentences. BERT, which stands for bidirectional encoder representations from transformers, is one example. The key thing about BERT is that it processes each word in relation to all the other words around it, both to the left and right. This bidirectional approach helps it understand context really well.
Okay, so BERT is like a super smart reader that understands the nuances of language. What did the researchers actually do in this study?
They collected a corpus of over 1,600 argumentative essays from Chinese EFL learners. That's English as a foreign language. These essays were then annotated, meaning each sentence or T-unit was labeled with its argumentative move type. They had human experts do this, and then they trained BERT to do the same thing.
A T-unit? What's that?
Good question. A T-unit, or minimal terminable unit, is basically the smallest grammatically complete sentence. It's an independent clause with any attached subordinate clauses. They use T-units because it allows for a fine-grained analysis of the argumentative moves.
Okay, makes sense. So they trained BERT on these essays. What were the different argumentative moves they were looking for?
They focused on 6 main types: claim, which is the main assertion; data, which is the evidence supporting the claim; counterclaim, which presents an opposing view; counterdata, which supports the counterclaim; rebuttal, which responds to the counterclaim; and non-argument, which is irrelevant or incomprehensible text.
So it's like a debate in written form. Claim, evidence, opposing view, response to the opposing view. How well did BERT perform in identifying these moves?
Pretty well. The overall F1 score was 0.743, which is a measure of accuracy. It means BERT was able to identify and classify the argumentative moves with reasonable reliability. They even said it surpassed existing models in the field.
That's impressive. What's an F1 score, though?
The F1 score is a way to measure a model's accuracy, balancing precision and recall. Precision is about how many of the moves BERT identified as a specific type were actually that type. Recall is about how many of the actual moves of that type BERT correctly identified. A high F1 score means the model is both precise and captures most of the relevant instances.
Okay, so BERT is doing a good job. But what's the point? How is this useful in the real world?
That's where the application part comes in. They used BERT's annotations to see if they could distinguish between different levels of writing quality and track individual learners' development over time. Basically, can AI tell a good essay from a bad one, and can it see how a student's writing improves throughout the year?
And could it?
Yes, to some extent. They found that higher quality essays had a higher ratio of counterclaims, counter-data, and rebuttals. This suggests that better writers are more likely to acknowledge and address opposing viewpoints. They also saw that over time, students increased their use of data and counterclaims and decreased non-argumentative text. This indicates development in their argumentative writing skills.
So the AI is not just grading essays, but also providing insights into what makes a good argument and how students improve. That's pretty powerful.
Exactly. It's about using AI to enhance language education, making it more data-driven and personalized. Imagine being able to give students targeted feedback based on their specific argumentative move usage.
This reminds me of the Toulmin model of argumentation. Is that related?
Absolutely. The study explicitly mentions Toulmin's model. It's a framework that breaks down arguments into components like claim, data, warrant, backing, qualifier, and rebuttal. This study was guided by Toulmin's model, using it to assess the logical structure of the arguments.
So what are the limitations of this study? Are there any drawbacks to using PLMs for writing evaluation?
Definitely. The researchers acknowledged that BERT struggled with certain types of argumentative moves, particularly counter data and rebuttal data. This might be because there weren't enough examples of these moves in the training data. Also, learner language can be messy with grammatical errors and unconventional usage, which can throw off the model. Plus, it's important to remember that this study focused on EFL learners, so the results might not generalize to other populations.
Right, the model needs to be trained on diverse data to be truly effective. So what's the big takeaway here?
The big takeaway is that PLMs have the potential to revolutionize writing assessment. They can provide detailed feedback, uncover patterns in student writing, and offer valuable insights for instruction. However, it's crucial to address the limitations, particularly in handling learner language and ensuring sufficient training data. It's about finding the right balance between AI and human expertise to create a more effective and personalized learning environment.
This is fascinating. It sounds like AI can be a powerful tool for educators, but it's not going to replace them anytime soon. It's more about augmenting their abilities and providing them with data-driven insights.
Precisely, it's about using AI to enhance, not replace, human expertise in language education. All right, let's dive into this paper. From Trial to Triumph, Advancing Long Video Understanding via Visual Context, Sample Scaling, and Self-Reward Alignment. It's all about making AI better at understanding long videos, which is a tough nut to crack.
Definitely. Long videos are a challenge. Current AI models can only process a limited number of frames at once, potentially missing crucial information. So, what's their approach to tackle this?
They're proposing a method that generates multiple predictions by sampling different visual contexts, and then uses a scoring mechanism to pick the best prediction. Think of it like this. Instead of just showing the AI one set of snapshots from the video, they show it several different sets and let it make multiple guesses.
Okay, I see. So it's like getting a second, third, or even 10th opinion. But how do they decide which opinion is the best?
That's where the self-reward system comes in. It's a combination of 3 scores. First, there's a frequency score, which basically counts how often each answer appears in the different predictions. The more frequent, the more likely it's correct.
Makes sense. It's like majority rules. What's the second score?
The second is a marginal confidence score. This reflects how certain the AI is about each of its predictions, looking at the difference in confidence between its top choices. It's trying to gauge how sure the model is about its answer within each sample and across different samples.
So it's not just about what the AI thinks is right, but how strongly it thinks it's right. Got it. And the third score?
The third is a reasoning score, which adapts based on the type of question. For global questions that require understanding the whole video, they use a clue-guided answering approach. For local questions that focus on specific moments, they use temporal self-refocusing.
Okay, break that down a bit. What's clue-guided answering and temporal self-refocusing?
Clue-guided is for those big-picture questions. They use video narration combined with a text-only large language model to reason about the video's overall content. It's like having the AI summarize the video and then answer the question based on that summary.
And temporal self-refocusing?
That's for questions about specific moments. The AI uses its own confidence levels to pinpoint the most relevant segment of the video and then focuses on that segment to generate an answer. It's like the AI is saying, okay, I'm not sure about the whole video, but I think this part is important, so let's look closer.
So to recap, they're sampling different frames, generating multiple answers, and then using a combination of frequency, confidence, and tailored reasoning to pick the best answer. Sounds pretty clever. What kind of results did they get?
The experiment showed that this approach significantly improves the performance of several multimodal large language models on long video understanding tasks. They tested it on 7 different datasets and saw consistent improvements.
That's impressive. So what are the key takeaways from this research?
The big one is that scaling visual frame sampling can significantly improve long video understanding. By generating multiple predictions and then intelligently selecting the best one, they found a new way to tackle the challenge of limited frame processing. It also highlights the importance of combining different scoring methods to accurately select the optimal prediction.
It sounds like a promising step forward in making AI better at understanding the dynamic world around us through video.
All right, let's dive into this paper. Grammar and gameplay aligned RL for game description generation with LLMs. Sounds like a mouthful, but it's all about getting AI to write game rules that actually make sense and lead to fun gameplay.
Exactly. So the core problem they're tackling is game description generation, or GDG. This is where you feed a large language model, or LLM, some natural language text, and it spits out a game description written in a game description language, or GDL. Think of GDL as a programming language specifically for games.
Okay, so why is this important? Why not just have humans write the game descriptions?
Well, GDL is machine readable. This means game engines can easily understand and simulate games described in GDL. This is super useful for things like automated game design, where you want AI to experiment with different game rules and see what works.
Got it. So the AI needs to be able to translate human language into this machine-readable GDL. What's been tried before?
Previous attempts have used LLMs, which are great at understanding context. They can even learn from a few examples. But the big challenge is getting the AI to accurately reproduce the actual game features. It's not enough to just generate grammatically correct GDL. The rules need to lead to a playable and interesting game.
So how does this paper try to solve that problem?
They propose a method called RLGDG, which stands for Reinforcement Learning-Based Fine-Tuning of LLMs for GDG. The key is using reinforcement learning to fine-tune the LLM, rewarding it for both grammatical correctness and how well the generated game description captures the intended game concepts.
Reinforcement learning, huh? So it's like training a dog with treats?
Pretty much. They give the LLM rewards for good behavior. In this case, the rewards are based on 2 things: grammar and game concepts. The grammar reward checks if the generated GDL is actually valid according to the GDL's rules. The concept reward evaluates how well the generated game matches the intended gameplay. Things like board cell usage, the number of possible moves, and so on.
Okay, that makes sense. So it's not just about writing code that compiles, it's about writing code that creates a fun game. What's this 2-stage training strategy they mention?
That's important. They use a 2-stage process. First, they use supervised fine-tuning, or SFT. This is where they train the LLM on a dataset of natural language descriptions and their corresponding GDL code. This helps the LLM learn the basic grammar and structure of GDL.
So SFT is like teaching the AI the basics?
Exactly. Then, after SFT, they use reinforcement learning-based fine-tuning, or RLFT. This is where the rewards come in. By starting with SFT, they avoid the LLM generating completely random and nonsensical code during the early stages of RLFT. It gives the RL a solid foundation to build upon.
Smart. So what kind of GDL are they using?
They're primarily using Ludi GDL. Ludi is a system that can represent over 1,000 different games, including board games, card games, and dice games. It's very versatile, which makes it a good choice for this kind of research.
And how do they actually measure these game concepts for the concept reward?
They use something called concept values, which are features of a game that can be quantified. They look at things like the percentage of moves with multiple options, the percentage of the board that gets used, the percentage of games that end in a timeout, the balance between player win rates, and the percentage of games that actually have a winner.
So they're trying to capture the essence of the game in these numbers.
Precisely. They then compare these concept values between the generated game and the ground truth game. The closer the values, the higher the reward.
What about the actual reinforcement learning algorithm they use?
They use GRPO, which stands for Group Relative Policy Optimization. It's a variant of Proximal Policy Optimization, or PPO, which is a popular RL algorithm. GRPO is particularly good for fine-tuning LLMs because it uses rewards from multiple sampled outputs for each query, which helps to stabilize training.
Okay, so they're throwing a bunch of different versions of the game at the algorithm and seeing which one gets the highest score?
Exactly. It's like trying out different tweaks to the game rules and seeing which ones lead to the most fun and balanced gameplay.
What were the results? Did this RLGDG actually work?
It did. Their experiments showed that RLGDG significantly outperformed baseline methods that only used supervised fine-tuning. It improved both grammatical correctness and the fidelity of the game concepts. The generated games were more likely to be compilable, playable, and actually resemble the intended game.
That's pretty impressive. So, what are the limitations? Where can this research go next?
One limitation is that the improvements were less pronounced in game categories where there wasn't much training data. So future research could focus on generating synthetic data or using data augmentation techniques to expand the training dataset. Also, they could try using larger language models, which might be able to learn more complex game concepts.
So the future is AI designing AI games?
Potentially. This research is a step towards that. By enabling AI to generate high-quality game descriptions from natural language, it could really help game designers and engineers in AI-driven game development.
All right, let's dive into this paper, Towards Automatic Continual Learning, a Self-Adaptive Framework for Continual Instruction Tuning. It's all about making large language models, or LLMs, learn new things without forgetting what they already know. This is continual learning, a hot topic right now.
Exactly. And this paper tackles a specific type of continual learning called continual instruction tuning. So instead of just feeding the model more data, they're focusing on giving it specific instructions to improve its performance. But the key here is automation, right? Making this process hands-free.
Spot on. The authors point out that current methods mostly focus on retaining old knowledge. This paper shifts the focus to selecting the right new knowledge to learn. They're trying to automate the process of filtering out the noise and only feeding the LLM the good stuff.
Okay, so data quality is a big deal. They mention that in domain-specific areas like medicine, getting high-quality data is tough because of privacy and the cost of expert annotation. They also bring up synthetic data, which is artificially generated data, but it can be redundant or low quality.
Right? So the core idea is to dynamically filter the incoming data. They use a proxy model, a smaller, faster version of the main LLM, to estimate how useful each piece of data is. This proxy model uses something called perplexity to figure this out.
Perplexity? Got it. It's basically a measure of how surprised the model is by a given piece of text. Lower perplexity means the model finds the text predictable, while higher perplexity means it's more surprising or novel. So they're using this to gauge the instruction following difficulty, or IFD, of each data point.
Precisely. A high IFD score means the instruction is really helping the model generate the response. A low score suggests the instruction isn't adding much. But here's the kicker. They don't just use a static proxy model. They update it along with the main LLM. This is what they call their self-adaptive framework.
Ah, that's clever. So as the main model learns, the proxy model also learns, and its filtering criteria evolve. This helps it identify redundant information and adapt to changes in the data distribution over time. It's like the filter is constantly recalibrating itself.
Exactly. They also address some practical deployment challenges. They want to be able to update the LLM without interrupting the service, and they want to be able to roll back to a previous version if something goes wrong. It's all about making continual learning a seamless process.
So the system has four main parts: data generation, data filtering, model tuning, and model evaluation. They use chain of thought, or COT, prompting during data generation to make the model's reasoning more transparent. COT is where you prompt the model to explain its reasoning step by step, right?
That's right. It helps ensure the model isn't just spouting out answers, but actually thinking through the problem. Then the data filtering module uses length, semantic diversity, and perplexity to weed out the bad stuff.
Okay, length is straightforward. They're just getting rid of super short responses. Semantic diversity is interesting. They're using cosine similarity between sentences to make sure the responses aren't just repeating the same information over and over.
Yep. And then comes the perplexity-based filtering, using that IFD score we talked about. Finally, they use parameter-efficient fine-tuning, or PEF, methods like LoRA to update the model without retraining the whole thing. LoRA stands for low-rank adaptation, and it's a way to train only a small subset of the model's parameters, making the process much faster and more efficient.
And for model evaluation, they use either direct accuracy evaluation if they have a validation dataset, or they use another LLM as a judge to compare the candidate model's responses to the current model's responses. It's like an AI bake-off.
Haha, exactly. They tested this in a real-world medical scenario using a synthetic dataset of medical consultations. They found that their system reduced computational costs by 66.7% while actually improving model performance. That's a huge win.
That's impressive. So by dynamically filtering the data and updating the proxy model, they're able to train more efficiently and effectively. It sounds like a promising approach for making continual learning more practical, especially in domains where data quality is a major concern.
Definitely. They even acknowledge some limitations in future work, like exploring how to use the filtered-out data for model alignment using direct preference optimization, or DPO. DPO is a technique where you train a model to directly optimize for human preferences rather than trying to predict a reward signal.
So instead of just throwing away the data that didn't make the cut, they're thinking about using it to further refine the model's behavior. It's all about squeezing every last drop of value out of the available data.
Exactly. Overall, this paper presents a really interesting and practical approach to automatic continual instruction tuning. The self-adaptive data filtering framework seems like a key innovation, and the results in the medical domain are definitely encouraging. All right, let's dive into this paper on omniscience, a domain-specialized LLM for scientific reasoning. It looks like these researchers are tackling a big problem: how to make language models truly useful for scientific discovery.
Exactly. General-purpose LLMs are impressive, but they often stumble when faced with the nuances of scientific language and complex concepts. So what's omniscience's approach to solving this?
They've got a three-pronged strategy. First, they use domain adaptive pre-training, or DAPT. Think of it as giving the model a crash course in science by feeding it a massive diet of scientific literature.
Okay, so it's like taking a general language model and fine-tuning it on a mountain of scientific papers. That makes sense. What's next?
Next up is instruction tuning. This is where they teach the model to follow specific instructions related to scientific tasks. So instead of just understanding scientific text, it learns to do things with that knowledge.
Like what kind of tasks?
Things like answering scientific questions, summarizing research papers, and even generating hypotheses. It's about guiding the model to perform domain-specific tasks effectively.
Got it. So pre-training gives it the knowledge base, and instruction tuning teaches it how to use that knowledge. What's the third piece of the puzzle?
Reasoning-based knowledge distillation. This is where it gets really interesting. They fine-tune the model using a special dataset designed to enhance its reasoning abilities. It's like giving it extra training in logic and problem-solving.
So it's not just about knowing facts, but also about connecting the dots and drawing conclusions. How does this distillation process actually work?
They use a high-quality reasoning dataset originally derived from DeepSeek R1 reasoning traces. By fine-tuning on this dataset, they transfer DeepSeek R1's reasoning capacity into omniscience.
That's clever. It's like learning from a master reasoner. So with these three components, what kind of performance are we talking about?
Omniscience is competitive with state-of-the-art large reasoning models on benchmarks like GPQA Diamond and domain-specific battery benchmarks, and it outperforms other models with similar parameter counts.
Impressive. So it's punching above its weight class. What's GPQA Diamond, by the way?
It's a challenging benchmark designed to test a model's ability to answer complex graduate-level questions. It's a good test of scientific reasoning.
Okay, that gives me a good sense of its capabilities. The paper mentions applying omniscience to battery research. How does that work?
They developed a battery agent that can rank molecules as potential electrolyte solvents or additives. This could really speed up the discovery of new battery materials.
That's a great example of how a specialized LLM can have a real-world impact. So instead of researchers manually screening thousands of molecules, omniscience can narrow down the search to the most promising candidates.
Exactly. It's about making the research process more efficient and targeted. The paper also highlights the importance of domain-adaptive pre-training and reasoning-based knowledge distillation through ablation studies.
Ablation studies, what are those?
They're experiments where you remove certain components of the model to see how much they contribute to the overall performance. In this case, they showed that DAPT and reasoning distillation are crucial for achieving top results.
So it's not just about having a big model, but also about training it in the right way. What about retrieval augmented generation, or RAG? Does omniscience use that?
They acknowledge that RAG can boost performance by allowing the model to access external knowledge sources. While their main focus was on training the model weights, they also demonstrated the power of omniscience in a full agentic setup with RAG for ranking molecules.
Okay, so it's a best of both worlds approach. Train the model to be smart, but also give it the ability to look things up when it needs to. What's next for omniscience?
They plan to refine it further using domain-specific reasoning distillation. This means creating a data set of questions specifically related to battery research to improve its reasoning abilities in that area.
That makes sense. The more specialized the training data, the better the model will perform in that specific domain. Any other future directions?
They also want to explore using reinforcement learning to further improve its performance. The idea is to train the model to make decisions that lead to the best outcomes in scientific tasks.
So, it's about teaching the model to not only reason, but also to act strategically. Overall, omniscience seems like a significant step towards creating AI tools that can truly accelerate scientific discovery.
Wow, that was quite the journey through the world of AI. From grading essays to designing games and even accelerating scientific discovery, it's amazing to see how quickly things are evolving.
Absolutely. It's fascinating how AI is being used not just to automate tasks, but to provide deeper insights and enhance human capabilities. That essay grading system, for example, isn't just about replacing teachers, but about giving them better tools to understand student writing.
And that long video understanding research really highlights the challenges of processing complex real-world data. The way they're sampling different frames and combining multiple scoring methods is a clever approach.
Definitely. And who would have thought AI could learn to write game rules that lead to fun gameplay? The reinforcement learning aspect of that research is particularly interesting, rewarding the AI for both grammatical correctness and engaging game mechanics.
It's also encouraging to see progress in continual learning, where AI can learn new things without forgetting the old. That self-adaptive framework for filtering data seems like a key innovation, especially in domains like medicine where data quality is crucial.
And finally, that domain-specialized model for scientific reasoning, omniscience, is a great example of how AI can be tailored to specific fields to accelerate discovery. The potential for AI to help us find new battery materials is really exciting.
It really is. It feels like we're just scratching the surface of what's possible. As these models become more sophisticated and data becomes more readily available, who knows what breakthroughs we'll see next?
Exactly. It's a constantly evolving landscape, and we're excited to keep exploring it with you. Thanks for joining us on this episode, and we'll catch you next time for more AI by AI.